Welcome back to the deep dive. So you probably think of your eyeball as, well, pretty stable, right? Like a fixed camera lens.
Yeah, most people do, just sort of sitting there, unchanging.
But today we're diving into some fascinating research that turns that whole idea on its head.
That's right. It turns out the human eye is incredibly dynamic. It actually undergoes these predictable, pretty significant changes in size and pressure every single day, every 24 hours.
You mean my eye is literally getting longer and shorter during the day?
Pretty much, yeah. We're talking measurable physical changes.
Okay, let's unpack this. It sounds like a really fundamental biological rhythm. So our mission today is to look closely at a key study.
Right, a study that tracked 15 young, healthy adults. Importantly, they had near-perfect vision, what we call emmetropic.
And they measured all sorts of things simultaneously, over a full day.
Exactly. Axial length, that's the eye's length, intraocular pressure, or IOP, and other things like corneal thickness, all tracked over 24 hours to see the peaks, the troughs, how everything interacts.
Now, before we get into the findings, you mentioned something about the methodology being key here, something about measuring pressure.
Yes, absolutely crucial. Measuring IOP accurately has always been tricky because the thickness of the cornea, the front surface of the eye, can interfere with the reading.
Oh, right. And doesn't corneal thickness also change during the day?
It does. It swells overnight.
Yeah.
So you've got this variable interfering with the very thing you're trying to measure, which
Yeah.
also varies. So,
Yeah.
well, it's been a problem.
A total mess of variables.
Exactly. So this study made a smart choice. They used something called the Pascal Dynamic Contour Tonometer, or DCT.
DCT, is it?
And the big advantage of the DCT is that it's designed to measure IOP in a way that's much less affected by how thick the cornea is at that moment.
Ah, so it helps remove that confounding factor. It lets you see the real pressure changes more clearly.
Precisely. It's really the only way to properly isolate how pressure relates to the eye's physical length changes throughout the day.
Okay, that sets the stage perfectly. So let's dive into that physical change first. The axial length front of the cornea to the retina. How much does the eye actually stretch and shrink?
Well, the first thing is the change is definitely real.
Yes.
Statistically, it was highly significant. P equals 0.0006, so no doubt about it.
Okay, it happens. But is it a big change?
In terms of magnitude, the average change they saw peak to trough was 0.046 millimeters.
0.046 millimeters. So 46 micrometers.
36 micrometers, yes.
46 micrometers sounds incredibly small. Like less than a human hair's width, right?
It is small in absolute terms, sure. But think about the eye as an optical system. Tiny changes in length can shift the focal point quite dramatically. So optically speaking, 46 micrometers of daily change is, well, it's a lot of oscillation.
Right. It implies the eye has to be constantly adapting somehow to maintain clear vision despite the structural wobble.
Exactly.
Yeah.
Especially for these subjects who are emmetropic, meaning their eyes focus light perfectly on the retina. A 46 micrometer daily shift is significant for maintaining that precision.
And when does this happen? Is the timing random or is there a pattern?
Oh, definitely a pattern. That's another key finding. The eye's physical length tends to peak around midday.
Midday, like lunchtime.
Yeah, their modeling put the acrophase, this sort of calculated peak time, around 11:14 a.m. The actual measured maximum often fell in the 1:0 p.m. session.
Okay, so longest around the middle of the day and shortest.
That happened much later, in the evening. The minimum length was typically measured around 10:03 p.m., basically as people were winding down for sleep.
Huh. So your eye is literally longest during your workday and shortest right before bed. Wild.
It is pretty wild when you think about it.
Okay, so the big question then, is this just the eye passively swelling up because of internal pressure changes? Like pumping up a tiny biological balloon?
That's the natural next question, and it leads us straight to intraocular pressure, the IOP. We already know IOP isn't constant. It changes over 24 hours, too.
And did this study confirm that?
Absolutely. They found significant diurnal IOP variation, P less than 0.0001. The average change, peak to trough, was about 3.12 millimeters of mercury.
3 millimeters of mercury. Okay. And the timing, did that line up with the length change?
It lined up quite well, actually. The IOP generally peaked in the morning around 10.23 a.m. on average. So just a little bit before that peak in axial length we talked about.
Okay, so pressure peaks first, around 10.23 a.m., and then the eye gets slightly longer, peaking around 11.13 a.m. or 1 p.m.
That's the pattern they observed.
That looks like a pretty straightforward mechanical relationship, doesn't it? Pressure goes up, the structure stretches slightly in response.
It does suggest that. And the data backs up a direct link. They found a statistically significant positive correlation between the change in IOP and the change in axial length.
Meaning when pressure went up, length increased.
Exactly. R equals 0.37, where P equals 0.001. So higher pressure correlates with a longer eye, lower pressure with a shorter eye. It definitely supports that hypothesis of passive expansion and contraction.
Right, the globe just sort of flexes with the pressure. Did they quantify that? Like, how much does the eye stretch for each bit of pressure increase?
They did. They calculated the regression coefficient, which basically tells you that relationship. They found it was about 0.00059.
Okay, what does that mean in practical terms?
It means that for every 1 millimeter of mercury change in IOP, the axial length changes by approximately 5.9 micrometers.
5.9 micrometers per millimeter of mercury. Okay, that's a specific mechanical property they measured.
It is a really interesting insight into the eye's biomechanics.
Okay, so now we can test the passive balloon idea directly. You said the average total daily pressure change is about 3.12 millimeter Hg.
That's right.
And each millimeter Hg causes about 5.9 micrometers of length change. So if we multiply those, 3.12 times 5.9, what do we get?
Let's see, that comes out to roughly 18.4 micrometers. Let's say 18 micrometers.
18 micrometer. Okay, wait a minute. 18 micrometers is the calculated length change based on the pressure swing. But you said earlier the total measured change in axial length was 46 micrometers.
Correct.
That doesn't add up. 18 is way less than 46.
Exactly. And this is where the study gets really interesting, maybe even revolutionary.
So the pressure change, even though it's correlated, only explains a fraction of the eye's daily size change.
A surprisingly small fraction. If you do the math, 18 micrometers out of 46. That's only about 39%. Wait, let me recheck the paper's calculation. Right, they analyzed the variance slightly differently. Their R-squared value suggests IOP variance explains about 14% of the axial length variance.
14%, one.
Yeah, 14%.
So there's a massive, like 86% of the daily change in the physical size of the eye that is not accounted for by changes in intraocular pressure.
Precisely. We have this huge gap. The pressure link is real, it's statistically significant, but it's only a small part of the story.
Wow. That is genuinely astounding. It completely changes the picture. It means most of the daily lengthening and shortening isn't just passive hydrodynamics. It must be something active, some internal biological process driving it.
That's the necessary conclusion. The eye isn't just passively reacting. It seems to be actively modulating its own size on a daily cycle. And pressure is only a minor contributor to that change.
So what could be causing that other 86%? What are the leading theories or candidates the research points to?
Well, the main suspects involve parts of the eye that can actively change their volume or perhaps their stiffness. The first big one is the choroid.
The choroid, that's the layer behind the retina, right? Full of blood vessels.
Exactly. It's highly vascular. And we know from animal studies that blood flow in the choroid can change quite rapidly. If the choroid swells up with more blood or constricts,
it would physically push the retina forward or let it settle back, changing the measured axial length.
Precisely. So the eye's length might be changing not because the whole globe is stretching, but because this internal layer is actively changing its thickness, like a sort of hydraulic sponge.
Okay, that makes sense. An active internal volume change. What else?
The other main candidate involves the sclera itself.
The white structural wall of the eye.
Yes. Again, mostly from animal work so far, but there's evidence suggesting the sclera isn't totally inert. There might be diurnal changes in its actual properties, things like the synthesis of molecules called proteoglycans.
And those affect tissue hydration and stiffness?
They can, significantly. So the idea is the sclera itself might be subtly changing its mechanical properties, its stiffness or hydration over the 24-hour cycle, contributing to the overall length change independently of IOP.
So we're looking at a combination of like internal plumbing, the choroidal blood flow, and maybe the structural wall itself actively changing its material properties day in and day out.
That seems to be where the evidence is pointing. It makes the eye seem much more like a complex, active bioreactor than just a simple static camera.
Absolutely. The IOP is part of it, yes, but the bulk of this daily size fluctuation seems driven by these other sophisticated, internally clocked biological processes acting on the eye's structure.
Exactly.
Okay, let's move forward then. We've looked at the back of the eye, axial length, and its connection to pressure. What about the front of the eye? Did things like the cornea and the anterior chamber also show these 24-hour rhythms?
Oh, they absolutely did. And interestingly, they showed rhythms that were distinct from the axial length and IOP changes, highlighting multiple sort of independent clocks running at the same time.
Okay, so let's start with the cornea. Central corneal thickness, or CCT, did that change much?
Yes, quite significantly. P less than 0.00001 again. The average daily change was about 0.018 millimeters, so 18 micrometer.
18 micrometers. And we already touched on this. The cornea tends to swell overnight, right? Because the eyelids are closed, less oxygen.
Correct. And the timing in this study confirmed that perfectly. The CCT was thickest right after waking up at the 6.00 a.m. measurement.
And this is where using that special DCT tonometer really paid off, right?
Exactly. Because if they'd used an older method, that 6 a.m. corneal swelling would likely have artificially boosted the IOP reading at that time.
Making it look like pressure was super high in the morning, partly because the cornea was thick.
Right. But because they used the DCT, they could check if the CCT changes were messing with their IOP results.
Yeah, and
They found no significant association between the change in CCT and the change in IOP measured by the DCT. The correlation was very low, R0.14, and not statistically significant.
So that confirms it. The DCT did successfully measure the real IOP dynamics without being significantly thrown off by that morning corneal swelling.
It's a major validation for using that technique to understand true diurnal pressure, a big win for the study's methodology.
Okay, very clear. Now, what about the space behind the cornea, the anterior chamber depth, or ACD? That's the distance from the back of the cornea to the front of the lens.
That also showed significant diurnal change, P equals 0.0368. And the amplitude was actually quite large, an average change of over 70 micrometers, 0.073 millimeters.
70 micrometers, wow. And its timing. Did it peak midday like axial length or morning like IOP?
Neither, actually. This is where it gets really interesting. The ACD's rhythm was significantly out of phase with both axial length and IOP.
Out of phase, meaning its peaks and troughs didn't line up with the other.
Exactly. The anterior chamber was actually at its deepest in the evening, peaking around 7.13 p.m. in their models. And it was shallowest right after waking up at that 6.0 DM measurement.
Wait, shallowest at 6 a.m., that's exactly when the cornea is thickest from overnight swelling.
Precisely.
So does that mean the cornea isn't just swelling outwards, but it's swelling backwards into the anterior chamber space?
That's the strong implication. The cornea swells, particularly posteriorly, pushing back and making that fluid-filled space shallower right when you wake up.
It just shows how interconnected everything is, but also how different parts follow their own distinct daily schedules.
It really does. You've got multiple independent, significant 24-hour biological clocks ticking away inside your eye, all coordinated somehow.
This knowledge really changes the game for how we should think about eye health. Let's talk clinical implications. How does knowing about these daily rhythms affect our understanding of eye growth, maybe things like nearsightedness?
It's potentially huge for understanding myopia. There's a process called emmetropization. That's how the eye naturally tries to control its growth to maintain sharp focus. It relies on complex biological signals.
Okay.
And animal studies have already strongly linked the amplitude and the timing of these daily ocular rhythms directly to whether the eye grows correctly or grows too long, leading to myopia.
So if someone's natural daily eye rhythm is off, somehow maybe their eye doesn't shrink enough at night, or it peaks too much or too little during the day, that could disrupt the signals controlling growth.
That's the hypothesis. If the rhythm is dampened or shifted or exaggerated, it might send the wrong signals, contributing to the eye growing too long.
And have we seen hints of this in humans before?
Yes, there have been previous studies showing that people who are myopic actually exhibit different diurnal patterns of IOP compared to people with normal vision. This new research, by clearly defining the normal healthy rhythm for axial length, IOP, CCT, and ACD in emmetropes,
gives us a much better baseline to compare against, to figure out which specific rhythmic differences might be driving myopia in those individuals.
Exactly. It helps pinpoint where things might be going wrong in the signaling.
Okay, that's eye growth. What about glaucoma? IOP is central to glaucoma.
This is probably the most immediate and practical clinical implication. We know that fluctuations in IOP over the day are a major risk factor for glaucoma getting worse.
Right. Big pressure swings are bad for the optic nerve.
Correct. But historically, if a doctor measured high IOP in a patient early in the morning, there was always that question, is this really high pressure? Or is it just the cornea being thicker and artificially inflating the reading from an older tonometer?
The confounding variable we talked about.
Yes. But this study, by demonstrating that the DCT technology can measure IOP reliably despite changes in corneal thickness.
It gives clinicians more confidence that they're seeing the true physiological pressure.
Exactly. It strengthens the case for using measurement techniques like DCT that aren't fooled by CCT changes. This allows for a much clearer artifact-free assessment of the actual pressure stress the optic nerve experiences throughout the entire day.
Which should lead to better diagnosis and better monitoring of glaucoma progression.
That's the goal. More accurate data leads to better clinical decisions.
Makes sense. Before we wrap up, you mentioned they measured other things too. Did ocular pulse amplitude, OPA, which relates to blood flow pulses in the eye, show a daily rhythm?
It did, yes.
Hmm.
OPA also had a significant diurnal change, P0.00006. It was generally highest in the morning and lowest in the evening.
So similar timing to IOP.
Yes, and importantly, unlike the axial length finding, the changes in OPA were significantly correlated with the changes in IOP.
Ah, so the blood flow pulse seems to track the pressure changes more closely.
That seems to be the case. The interpretation is that the OPA variation is likely driven more by the same systemic factors affecting IOP, rather than being an independent driver of the structural changes like we suspect for choroidal thickness. It seems more like a pressure-related consequence.
Got it. Okay, so let's try to summarize this incredible deep dive.
Yeah.
The main takeaway is that our eyes aren't static objects at all. They are fundamentally dynamic.
Absolutely. Operating on these complex, coordinated 24-hour cycles affecting physical length, internal pressure, corneal thickness, anterior chamber depth. It's a whole system in constant, predictable flux.
And understanding these natural rhythms is clearly critical for understanding both normal vision and diseases like myopia and glaucoma.
Without a doubt. And it really brings us back to that big unanswered question, the mystery from the study.
The 86% gap.
The 86% gap, yeah.
The knowledge gap of the day.
Right. So given that we now know that the natural daily change in intraocular pressure only explains about 14%, just a small slice of the total daily change in the eye's physical length.
It leaves this huge, fascinating question for you, the listener, to ponder.
What active biological mechanisms are really doing the heavy lifting here? What's responsible for that other 86%? Is it massive, controlled swings in choroidal blood volume? Is it the scleral wall actively changing its own biomechanics day in and day out? Or something else entirely?
Figuring out that remaining 86%, that feels like where the next truly major breakthroughs in vision science are waiting to be discovered.
It certainly seems that way. A huge area ripe for future research.
Absolutely fascinating stuff. Thank you for joining us for this deep dive.
My pleasure.
We'll catch you next time.